Welcome to this episode of Real Chemistry. You never seen me outside before, but I got a new exciting experiment to tell you about, and I want to do it in a new setting. So I'm going to tell you about the Two-Slit Experiment, which is my favorite experiment in the history of all of science. To this day, people aren't sure exactly what to make of all of the results. In fact, I'll talk about that more in a follow-up video called The Measurement Problem and the Interpretation of Quantum Mechanics. So before we can get a handle on this experiment, which really changes the way we view reality, we need to understand waves. We could start with something simple like a water wave. So for example, take a look at these two waves. We have two different sets of waves coming from two different little center points there. And as those peaks and troughs come at each other, an interesting thing starts to happen. Where the two peaks overlap, we get what's called constructive interference. They add together, and that gives us a new higher peak. When a peak overlaps with a trough between those two waves, we get what's called destructive interference, and the height of our wave drops. So those are two types of interference that happens all the time with waves. Turns out we can do that with light too. So here you see this setup where you have a laser shooting the light at two slits, and then behind it you have this screen showing you what that light does. And you see all those stripes. Bright stripe, dark stripe, bright stripe, dark stripe. That's what we know of as an interference pattern. And that happens precisely for the same reason that water interferes. Waves of light are waves also. And so when the peak amplitude of a light wave overlaps with a peak, it gets brighter. If a peak overlaps with a trough, it gets darker. And the two slits there actually make it so that the light has to travel a different distance to get to the screen, which makes the peaks and troughs overlap differently, depending on where they hit on the screen. Now, if you don't get all that, don't worry. Just know that light waves give you interference patterns. Okay, now things start to get interesting. Let's say instead of shooting light, we shoot particles, electrons, little particles that go around our atoms, negatively charged. We think of them lots of times as like little balls orbiting the nucleus of an atom, kind of like in a solar system model. It turns out electrons are much more complicated than that. So if we were to shoot electrons at these two slits, what would we expect? Well, they're particles, they're not waves, so we shouldn't get an interference pattern. Instead, we'd see something like this, where behind each slit, we get a little pile of electrons. If the electrons hit anywhere on that screen with the two slits, where the slit isn't, they just get stopped by that screen. And that's it. There's no interference pattern. Here's the crazy thing. People have done this experiment with electrons. People have shot them at a screen, and do you know what they see? Ba-dang, an interference pattern. So first weird result for the two-slit experiment. Turns out electrons can behave like waves. This means the same thing to all scientists who saw it. They knew this was the electron, giving us that same bright, dark interference pattern. That means we have a wave. So that's pretty strange. Now, a lot of people, when they first see that, what they think is, okay, what's happening is electrons are going through those two slits, and they're all negatively charged, and they kind of push each other around, and we end up with some weird pattern. No, it's not what happens, because even if we stick the electrons through one at a time, so we get our electron gun firing electrons nice and slow, pew, we let it go through the slits, we let it hit the screen, pew, we do it again. We let that add up over time, even though there's only one electron at a time. What happens is we get that same interference pattern. This is bonkers. This is not what we expect. It means that our electron somehow has to pass through both slits. Why is that? Well, the only reason we get an interference pattern is because you have two separate sources of a wave. Just like in that water wave we looked at first, where we had two centers that the waves were emanating from, here we have two slits, and the waves come out of those slits. And the only way we get an interference pattern is if that wave is going through both slits. How can one electron go through both slits? Well, it turns out we describe an electron as a wave, and if we do that, well, a wave can go through two slits, no problem. But the confusing thing is we also want to think about the electron as a particle. And so what some people said when they saw this result is they said, okay, let's go measure which slit that electron goes through. Will we get that it goes through both? Will we get that it goes through one and somehow still makes an interference pattern? The results were stranger than they probably could have anticipated. If we measure the electron, we put a little detector next to the slit, and it will say, oh, it went through top slit, oh, it went through bottom slit. The interference pattern goes away. Let that sink in. So, what was behaving as a wave, when we watch it, behaves like a particle. why should it matter if we detect it? Normally in physics, we think, hey, we measure things all the time, it's not going to change what's happening to that system. Or if it does, it'll only change it just a little. But here, it's actually fundamentally altering the way that electron behaves. It goes from behaving like a wave to a particle, from interfering to just piling up behind those slits, exactly like we thought would happen. Exactly what would happen if you threw bowling balls down at two slits. They pile up behind those slits, and that's it. So what does this mean? This means that our electron sometimes behaves like a wave. It behaves like a wave when we're not measuring it. On the other hand, our electron can sometimes behave like a particle. It behaves like a particle if we do measure it. That bugs a lot of people. And if it doesn't bug you, it's maybe because you're bored and don't care. That happens too. But if you do care and you do pay attention and you do want reality to make sense, it seems weird that sometimes it behaves like an electron and sometimes it behaves like a wave. What do we do with that? Well, the weirdness there turns out to get even deeper, and that's what we'll talk about in the next video, the problem of measurement.